data scientists, do you do your own models, or do you mostly use, like when you think about AI, do you mostly use like prefabricated AI, or do you do your own? Prefabricated, except for Alan, who creates his own. Okay, so I'm actually going to talk. So I'm a developer, not a data scientist, but I have worked on quite a few data science projects and deep learning projects. So maybe I should actually call myself a data scientist. But as you'll see when we go through this, I take a very developer-centric approach versus sort of like going algorithm first. What I'm going to talk about is building a model from scratch, and specifically building a specific type of model that's called a video action detection model. So a typical video action detection model would be what Hank was talking about, like a video indexer, something that can say that at certain events at certain times in the video, something is happening, whatever that might be, like a person entering the scene or something like that. The type of projects that we've been working on with my team is one where we did crash detection. So this was for Formula One videos. We did crash detection to be able to do watts type video clips. So pick out like the time in the videos that had crashes. Or store monitoring, where we worked with the store to figure out so that they could classify when theft was happening in the store, and not necessarily for capturing or for catching a thief, but for understanding how that looked and how what they could do for, like, in order to reconfigure the store to basically put different kind of items in different locations and not have as much theft. Or age classification of movies, so figuring out where there was violence or sex or these kind of things. So all of these fall into the umbrella of video action detection. And I'm going to talk about a very specific case that we've been working on, which is a highlight reel for soccer. So in this case, we're working with a customer who's creating UEFA game videos for ESPN and the like. And as you've probably seen, if you watched a soccer game or any kind of game, you usually have like a highlight reel in the halftime, and then one after the game that shows like the most interesting parts of the game. So taking a match video and creating a highlight reel from it is it's like a super nice thing if you can do it sort of like unsupervised without having too much interaction from humans. But this, at least to me, when I started with this, it sounded like a kind of like an insurmountable task. It's very hard to even comprehend how you go about solving something like this. So the way we thought about it was, first we started with the things that you would typically do for any kind of software project and try to figure out what is it that we're actually trying to accomplish, what's the model going to look like, what's it going to predict, and so on. But apart from that, some other things that you need to think about when you're doing machine learning projects is how accurate does it need to be. So for different models, they might need different accuracies. Sometimes it might be good enough if you can get like 60% of the items correct, and sometimes you have to get 99.9, like fraud detection, for example. That would be horrible if you got like only half of them, and half of them, like, and you constantly got sort of like your credit card manufacturer to say, yeah, it's been fraud again, you need to return your card, these kind of things. And also, as I'm going to get to later, what does accurate actually mean? Because accuracy can be measured in many, many different ways. And also, what happens if we get it wrong? So let's say you have a model that predicts if someone should get a loan or not, and they don't get a loan. That's a pretty significant problem if they should have gotten a loan. So you have to think about sort of like the consequences of the actions. And you need to survey the data to actually understand if you have enough data for a machine learning model to learn. So in our case, we went through and thought about, okay, so what should our model actually do? We looked at how they did this manually first, and And the way they work, if you've been in one of these studios, is that you have a lot of people that sit throughout the game and click on buttons. Like every time there is a shot on goal, or there is an attack, or there is a red card or an injury, like they have all these buttons that they sit and click, and there's like 5, 6 people just employed to do like the clicking for stats and things in the matches. And they also have a lot of other things. For example, IR cameras on the goals, and different kind of cameras throughout like the big arenas that can tell them where the ball is, and all of these kind of things. And then when they go to create the highlight reel, they have some kind of expert system. So an expert system might be a human saying that, okay, so we're going to take a few of the shots on goal, all of the red cards, all of the injuries, and this is going to be our highlight video, or the basis of it at least. And this is how it worked. And then you can of course automate that maybe a little bit. So when we're thinking about, okay, so how can we replicate this without having all these people sit there and click the buttons, we can either do an all-in-one model, which is basically you take the video and out comes the highlight. This is sort of like a holy grail of models, but it takes a lot of data. In order for you to go from video to highlight directly, you would have to have a lot of match videos and a lot of matching highlight reels, and then for a model to be able to do the mapping. And we didn't have that much data, even though we did have a lot, because there simply aren't enough games. There aren't enough UEFA games in history to do a model like the previous one. But instead, we went back to look at like what did the original sort of like, what did they do when they did this manually? Well, they did this, and what if we created a model, or multiple models actually, that took each one of these events and said, hey, can you mark down in the video when you're seeing a shot on goal, or a red card, or an injury? And all of these models we could feed into the already existing expert system that they had, and then create the highlight. So this is what we went with in the end. And if we look at the specific task of figuring out when there is a shot on goal, the first thing you do in any kind of project like this is you do a data survey. So data survey means that you take a look at all of the data. If you've heard the term exploratory data analysis, these kind of things, basically you look through the data and you look and see how much do you have, how representative is it. By representative, I mean, for example, if we're going to create a model that should work not only for UEFA games, not only for male UEFA games maybe, but for female UEFA games, and maybe you need to make it work also for little league games, or whatever, then you need to make sure that you have the data that represents all the different sort of categories that you might want to predict on. So we ended up saying that we only have UEFA games, male UEFA games actually. So our model will currently only work for this scenario, but this is something where a lot of people fall short. They try to create a model, they have a very specific set of data, and they try to apply that model to something else that just it didn't represent, and therefore it's going to predict it wrong. And then we look at sort of like how good the data is, how good the labels are. In our case, the labels were very good, but we have to also think about, when we think about the goodness of the labels, did they actually click on the exact time that things happen? Because when you're talking about video, they might have clicked, in some cases 2 seconds later, or 2 seconds earlier, or whatnot. They might have mislabeled a lot of shot on goals as attacks, or these kind of things. So we need to clean these up and make sure that they're as accurate as possible. So then we went through and we thought, okay, so how are we actually going to kind of mark the video? Because you can't just sort of like bring in a video and say, and have it spit out, these are the 50 different times there was a shot on goal. So what we did was we took all the labels, and then we a label being there is a shot on goal at like 4:59. And then we took a clip and we made clips that were 5 seconds long and with the marking in the middle. So 5 seconds, 2 seconds, 2.5 seconds on each side. This is an arbitrary number, like the 2.5 seconds. It could have been 10 seconds on each side. We reason that 2.5 seconds gave us enough information. Like you can't take like a still shot because this might be a shot on goal or it might be an attack. Who knows? But only like when you put it in context, you will know if it was one or the other. And we reason that 2.5 seconds on each side gave us enough context to say if it was or not. We tried different versions of this actually. Then you have to go through and do something called negative sampling. So negative sampling, if you think about something that classifies a cat or not a cat, like you want to figure out if like, is this image a cat or not? Then you can't just feed it cats because then it has nothing to say, what is not a cat. And if you try to feed it like 500 images of cats and 500 images of black screens, then it's not going to learn what a cat is. It's going to learn what not a black screen is, right? So you have to have something that is not a cat, but similar enough to a cat that it actually has to learn the intricacies of cat and not a cat. So maybe not a cat is a dog, or maybe not a cat is a tiger if you're looking for a house cat or things like that. And actually the closer you can get to not a cat, like the closer you can get not a cat to a cat, the better off your model will be because the more the model will have to learn. So in our cases, we were thinking like, okay, so shot on goal, the most close thing is actually like an attack, but that was not necessarily making it all the way to the goal. And these kind of things we would have to kind of like figure out for each one of these. But negative sampling is a very, very important part of the process because let's say, for example, in Hanks, if all these categories are way, way different, if like all the if all the pictures of, I don't know which categories you had for your for your Lego images, but yeah, like, but let's say, did you have a poo maybe? What did you have as categories for your model? Like, yeah, but let's say what was one of your categories? Yeah, Marge Simpson. So if you would put all the Marge Simpsons on a blue background and all the Bart Simpsons on a red background, then it would also have not learned Marge versus Bert. It would have learned blue versus red. So this negative sampling or the selection is super, super important. And I put this picture here because typically like a negative sample would be the crowd. Like there's a lot of crowd pictures in soccer. And you don't want to have like all the negative samples be crowds because that's very easy to pick out. So then we went through and we tried to figure out, is there some way we can help the model along with things that we already know? Can we actually make models that use human intelligence to figure out whether or not it's a shot on goal? So we looked at a lot of the samples of shot on goal and kind of tried to classify what's special about them versus the samples of not shot on goal. So we discovered, for example, that the crowd was very loud when there was a shot on goal or when there was an interesting event. I should say that this was important then, and then suddenly became not so important during COVID. So building a model based on this knowledge is a little bit fragile. Like I will also say that this hint was the number was a really, really good hint. It gave us a really good accuracy, but it's also something that's very fragile and different because this wasn't representative of the games during COVID, for example. We also noticed that there was a certain like sort of speed to the players or speed of the movement on the field, and they were all, of course, moving towards the goal. We had a theory that if people were more huddled together, that was more representative in the samples that were shots on goal. So you had a lot of people, like you had the player, and then you had a lot of defenders around him or her, these kind of things. The goal was visible. Usually right after a shot on goal, there would be a scene change to the main player, or like to the player that would do the shot on goal. And then the player poses would maybe be important. We hadn't really figured out like how they would be important, but you can imagine that a shot on goal, like the player is in a certain position when they do the shots versus when they're just running around or filming or whatever. And then we took all of these and we did something called hypothesis-driven development. So this is actually something that I do in my other software engineering project as well, where I have a theory that, if I create a model based on sound, I should see a really good result. If I make a model based on something else that maybe is not so significant, I shouldn't see a good result. So I use this also in regular development projects where I say, I'm theorizing that using this way to copy files in Azure will be faster than this way. And then I do like the two examples and I juxtapose them against each other. So doing this for all of these things, first, before we get into how we actually test the ideas, let's go through some of the building blocks that we have, and some of them actually Henk have already talked about. So one of the building blocks is classification, like image classification. Is this a cat or is this not a cat? Like, is this a red card or not a red card? If we just feed in the image, any frame from the video. Object detection. So there are already pre-trained models for object detection that will tell us with very high accuracy whether this is a person, exactly where the person is. This is this is a sports ball, these kind of things. So we don't have to build a model to do this. We can just reuse a given one from before. We've seen that we can remove the background, for example, like to avoid, to completely remove maybe the audience and these kind of things. So you can focus on just the players. And if you do that, then there is a higher chance that you'll actually tease out like the movements of the players that make the difference. Face recognition is something we can do. We didn't use this at all, but and then poses, there are already pre-trained models for kind of giving you the pose. You can see in this case, it kind of picked up the other player. It doesn't really matter much. Like it's the average positions are useful. This is, by the way, my daughter playing basketball here. So these are my own pictures that I've used these things on. And you can even have like finger positions. So there are gesture models and things that you can use. One thing though, when you're trying to prepare these kind of thing, or when you're trying to extract these kind of things, is that some of these are a little bit expensive. And when I say expensive, I don't necessarily mean cost-wise, even though if you're using APIs and things, they might cost too. But if you're imagining that you would have to do object detection on every frame of every piece of the video, and sometimes actually in our case what we had 5-second intervals, but we didn't have 5 seconds and then 5 seconds. Instead we overlapped them, so we had like the middle part every second, so each video would actually overlap 5 times too. That takes a lot of time. So if you want to do this and you need to be ready by halftime, that's not going to happen if you're going to do like this kind of preparation on each of the videos. So you need to be a little bit cautious also about sort of your scenario and whether like how much pre-processing you can actually do. So in some cases, it's better to actually have something that's not a machine learning model, like actually use software. So this is from a project I was working with a hospital where we were doing trying to detect benign or malign um, cancer cells or cells. And in this case, they wanted to do machine learning to figure out sort of like where these cells might be. But in the end, we suggested to do regular color decomposition, basically say, because they inject this fluid that causes like some of the cells to turn purple or brown depending on the fluid. And what you can do is you can then basically just extract the ones that fall in a specific color spectrum. Maybe, you know, like between this and this pink type thing. And that's a very inexpensive thing compared to having a model predict these kind of things. And also it doesn't require any data because it's just a math equation. We can also do this, for example, for background extraction. So background extraction in general is fairly expensive operation. But what we can do instead, if you have a steady cam, this doesn't apply to the football case, but this applied, for example, to our case in stores. If you have a steady cam, then you can just simply look at all the pixels, and if they did not move between frames, then they are the background because, like essentially, like the person will move somewhat a little bit between the frames. So this is actually a very inexpensive and fairly accurate way to get the moving pieces out. You can also look at speed and direction. This is something called optical flow, based on like a very similar theme where it looks at a set of pixels. In this case, you would maybe do an object detection on like these lights, or you don't actually have to. The optical flow algorithm actually figures it out. And then because between a set of frames, the pixels will only move so much. This is like the nature of a video, unless you constantly change scenes. So the optical flow algorithm can follow the pixels and see sort of like what general direction this thing is moving in. Also assuming that you have a steady cam. So this is not something that you can necessarily use in a soccer game where you're panning around like this. And then for a scene change, you can just pick a random number of pixels. Let's say you pick, 200 pixels. And if enough percentage of them has changed in between two frames, you have a scene change. This is a very inexpensive scene change calculator. And there are many, many, many of these things that we sort of like as software engineers can actually figure out. Like some of them seem like, whoa, that's really genius. But some of them are like, once you get into the rut of doing like these kind of algorithms, they're not that complex. And they're definitely not complex to implement once you've come up with them, sort of. And there are many that are already pre-created, like convex hull to find like the surrounding pieces of an object, these kind of things. So now we can go ahead and test the ideas. So we went through and tested a loud crowd. So for this one, again, we theorized that if there was a loud crowd or if there would be certainly a difference between the shots and not shots. And for this, we didn't even need the video. We just needed the audio. And when we went through and we sort of like did a spectrum analysis. So this is in Python, there was like a library that could extract sort of like the maximum pitch and these kind of things. There was an absolute difference between the shots and not shots in our case. In fact, yes, with an audio model, we were able to reach around 85% accuracy with our accuracy measurement, I should say, yes, based on audio. So now, as I mentioned, after COVID, this became moot, but this was a big part of the model that we created. We actually created in the end a model that was a combination of multiple models working together, kind of like doing voting. It's called ensembling models when you take, one, for example, audio model and then couple that with a video model. And then like if you have If this one says yes enough, and this one also says a little bit yes, then it would be a yes, these kind of things. For the player density, what we did when we did our trial runs was, first off, we were going like, so how can we possibly figure out how many, like, if we have players huddling together? So we did this. We split up the picture in actually 100 sections, lengthwise. And then we did object detection to figure out where the players were. And then we said, okay, so mark down a 1 in each of the sections that we have a player. If we have 2 players in one of the sections, then there will be a 2, like the center position of this object box. And then what we did was we coupled all of these, and this is for 1 second, since there are 25 frames, but we actually coupled them for like 125 seconds. So this now created a heat map, and as you probably know, an image is just a set of like pixels that have numbers between 0 and 255. So these worked perfectly as images, and you can even sort of like take the range and sort of make it 0 to 255. And then we could use this just as an image and classify based on the image outcome of the video clip and say, was this or was this not a shot on goal? This was not very accurate. So this was like a failed attempt, but it's I'm adding it in here because there are going to be a lot of failed attempts, and there are a lot of things that maybe give you ideas for other things that you could possibly use this for. For this, we used object detection. Now, I think Henk already showed you how to do this with cognitive services, but there are already pre-trained models also that you can use locally. You just download a model and predict. This is from Keras. Keras is one of the bigger sort of like machine learning or deep learning frameworks to use. And this can predict 80 different categories, including person and sports ball. One of the problems we had with this was that if you've ever seen a UEFA game, the ball is not very big. Like it's usually like a speck, one like tiny like this, a white speck that that it's there because you're a human and you know where the ball should be and these kind of things, but it's very difficult for a model to pick out that white speck is a ball versus some other white speck that might be the audience, for example, especially if you don't want to have like super high res input. And if you have super high res input, it takes a lot longer to process. One thing to think about when you use pre-defined models is that depending on the data they've been trained on, if they haven't been trained on something that's representative to yours, you might get a situation like this where it tries to figure out the caption for this cricket game, but it's only been trained on US data. Like most of the models are trained on US and European data, and mislabels it as baseball players. So this is actually one of the big problems in machine learning, that you don't have representative data and therefore get unrepresentative results. For the speed and direction, we've already talked about optical flow. So optical flow is something that you can out of the box get. For example, in Python, there are several libraries to extract speed and direction from images or from video. Player poses, also similarly to the object detection, there are pre-trained models for this, either pose detection or gesture detection. And for the red card, we used image classification. And I just want to talk a little bit about how image classification works if you haven't seen it before. So when you build an image classifier, you put in a lot of data at the top, like a lot of images of cats and non-cats, or in this case, chihuahuas and muffins, and maybe some things that are not chihuahua or muffin. And then you build up a neural network with a set of layers. These layers, depending on how many you have and how big they are, can detect more or less detailed things. But in general, the way you should think about it is that the first type of layers, they detect very fuzzy things, like maybe a color or maybe a speck of um, like a pattern or things like that. And the more you go down the layers, the more they combine them into bigger features that might be important. Now, a machine learning model does not know anything about ears or noses or eyes or anything, so it will not say, hey, there is an eye in this picture or there is a nose in this picture, but it might have like a fuzzy um, feature that looks a little bit like an eye, and it might say it has, you know, 0.9 of this feature, these kind of things. And eventually, this lower layer is what you use to do the prediction on. Maybe a Chihuahua has like a lot of nosiness and like a lot of eyiness, whereas a muffin does not have so much of that. And these things, the way they look is like they have like these convolution layers. So each one of these layers, if we lay it on the side, is like a convolution layer, which is basically matrix multiplication, where you go like with a window over the image like this. And then in between, it compresses it a little bit, and then it does a new matrix multiplication level, compresses it, and eventually it gets these features like 0.9 eyiness, 0.2 nose, these kind of things. And then eventually it predicts based on that last thing that's just a number of features. To build one of these, surprisingly little code, to be honest. This is the code for building the whole neural network that we're seeing here. Obviously, you would have a lot more layers and these kind of things. And this tells you a little bit about how many, like how many convolutions, how big the windows are, these kind of things. And then you have something that trains it, and you train it then on some of your data, and you save some of your data for validation. So after you've trained a model, you can say, okay, so now check what results you get here, and the accuracy is like, how did it predict on those versus the real labels? All of this, if you want to get in and kind of do your own deep learning, this is an excellent book for doing that. And it is, like I said, surprisingly simple to do this. The problem is the data, not the model. Like the actual algorithm, as software engineers, like we know how to, like that's not the difficult part, let's say. But the problem is that you have to have a lot of data for this to get accurate. So if we look at something like this, in order for you to determine if it's a Chihuahua or a muffin, you would have to have a large number of layers, and the number of layers that you would have also dictate how much input data you have. So you might have to have, I don't know, 5,000 Chihuahuas and 5,000 muffins to even get like a semi-accurate result on this. I want to focus though on something, and I'm going to talk about like how you can make this a lot easier for yourself without having to do the 9 days of ChatGPT training that, or 9 days times 12. Did you say? I don't know how, or was it 4 times as much? Or I can't remember for ChatGPT 4. It was, anyways. That's not what we want to spend our time and money on. But the layer that we get at the end, the one where we can determine if it's a Chihuahua or a muffin, that's called an embedding. An embedding is sort of like this array of numbers that tell you different features. So it's called an embedding or an intermediate representation, or maybe we can even call it a secret code that kind of like classifies this image or what it might be. So what is an embedding? And I think that actually Alan is going to talk about similarity searches, and this uses this central concept in deep learning of embeddings quite a bit. So if we think about if we were to recommend a book, let's say we have a large set of books, and now I want to recommend a book either to my daughter or to my husband. Um, and I used to have to pick one. One of the things I could do is like I could sort them and say, and this is more for adults, this is more for youth. And maybe if I pick something from my daughter, she'll like the ones with the youth feature better than the adult feature, I think. So that's one way. Uh, we might also want to add in a new feature that's called fiction. And now we've placed sort of like all of these in a diagram where uh, they're like how old you have to be and whether or not you like fiction. And it turns out that when we put these on a scale like this, and we say, okay, so this is like a minus -06 and an 04, then things that are similar get stuck together very much in this sort of like in this universe. And now we don't only have two features, we have maybe a couple of other things like math references. How many math references are there? Is it US centric? Is it shitlet? Is it funny? Sci-fi, lawyers? Would Brad Pitt play a character in a movie? Like it could be whatever. In fact, machine learning does not have like a feature that's called like math references. It has a fuzzy feature that it figured out like that distinguishes these type of books from these type of books. And you might not ever be able to understand what that feature actually is because it doesn't make sense in the human world, but for a machine learning model, it makes sense because it can classify all of these things and separate them out. So this is, for example, FaceNet. FaceNet is a model that was used to for image similarity, taking like the image embeddings and figure out who, like, is this a picture of this person? So you could give it just a very few samples, maybe even just 1 or 2 samples of yourself, and then it could say, yes, this is you or this is not you when you take a new picture. And if you look at this is a way to represent 128 different features in one single image. So bear with me when it's like 2D from 128D. But you can see here, these are pictures of me, and they're all clustered together in this thing. In fact, when this model gets a picture of me and I ask it, who is it? It can say who it is because it knows like who it's more similar to. It will definitely know that it's me and not Bill Gates, as an example. And if we look at the pictures here of the people that I've chosen in the sample, we can see that there is definitely a certain similarity between the pictures that end up clustered together in this. Like the features of like more male with male features and female features and different hair colors and skin colors, etc. So this embedding and this clustering is extremely useful, and it's also what allows us to do one-shot learning, meaning that you can have a model that extracts the features for you, and then you can supply only one image of you, and it will know if it's you or if it's someone else in your list um, of people. So you can use this, for example, to determine like who it is based on um, a picture of all the people in your company, for example. So now what we did was we took these embeddings. So we created these embeddings from an already given model because you can also take them out and extract them. And then we put them together again, like we did with the thing where we had people close together, and we put them in one single image like this. So 125 rows, one for each frame in the 5-second video, and on each one of these, 1,024 different features or different embedding features. And it gave us something like this, which is, to a human, is like, okay, so what does this mean? How do I know if the first one is a shot on goal or not? Well, you will never know, but a machine learning model can actually figure this out because it knows sort of like that this specific picture looks like most of the shots on goal that I've seen, but this picture down here does not look like most of the pictures I've seen. Because to a machine learning model, they don't have to see visuals like humans do. They just do pattern recognition, right? They don't care. They don't know what a cat looks like. They know that a cat looks like very similar to these other things, like these other objects. So this is what we used, and it gave so one of these things might be grass. I don't know. Maybe this is a goal. I have no clue. It could be fussy background plus a light in the corner. Who knows? Like it actually doesn't have to make sense at all. The one thing we found that was very interesting was this: in some of these embeddings, we noticed these patterns, like you see the abrupt change in line, like the abrupt line here. What could this be? Yeah, exactly, right. So this is like a very nice view of like how how effective this thing is also at detecting scene changes. So we didn't actually have to figure out like manually what a scene change was. It already knows because this is an easy pattern for a machine learning model to pick out. Um, so when we then create a 3D CNN, a 3D CNN just means that we have 2D CNN is like height and width, and now height and width and time. We can create a model that just takes all the frames instead. This is not a VGT model, but another way of doing this. And we could go through and create a model like this. The problem is that these are also very expensive to create. And they're very expensive to train. But if we think about a scenario where we're doing image classification, and we want to do image classification to determine if it's a chihuahua or a muffin. Actually, a surprisingly hard task, to be honest. Turns out that we cannot use an existing model. There is no sort of cognitive service that will return chihuahua or muffin because that's not, well, I'm lying because they might actually be categories in, in cognitive search, but generally, like they are specific enough that they would not be. So what we can do then is we can do transfer learning. So this is sort of similar to what you would be doing on top of ChatGPT to fine tune it, or on GPT-3 or GPT-4 to fine tune it. You can do that on these image classification models too. And that was what Henk was showing with doing classification of Lego figures, because the model does not have Lego figures. So what you do then is you take a model that's already been created, that's kind of extract all these embeddings, and then you fine tune only the last layer. So you pick, in this case, I think this is a ResNet with this architecture, and not a ResNet that has already been trained by Microsoft or Google or Meta or one of the organizations with huge amounts of data. And you don't have to do that. You don't have to put in like the 9 days of training. You just have to put in like the hour of training that takes the embeddings and now classifies Chihuahua versus Muffin. This is a simple task. This requires much less data, like in fact, very little data. You can get away with like maybe 500 pictures and get super accurate result here. So transfer learning is the key to working sort of like on your own models. And for us, we could use there are actually pre-trained 3D CNNs also, pre-trained video CNNs that we could use. And we ended up in the end using one of these pre-trained 3D CNNs, generate a model out of it, and then also use our audio model and combine them together. So the last part, now you have your model and it's like a whooping 100% accuracy that Henk had. But what did it actually learn, Henk? Did it learn blue backgrounds? We don't know. So we need to kind of now survey a little bit what it actually got very good at and what it got not so good at. By maybe sending in a number of different videos, for example, that we would deem very hard, or maybe we could send in, we would send in, we would send in videos that were very hard to classify as humans and things like that. And we can also run different tests on it. Like there are different tools that we can use to figure out like which areas of the image did it focus on when it classified this as a cat or not a cat, these kind of things. So in our case, we wanted to make sure it didn't focus on scene changes, goals. In the shoplifter case, that it didn't focus on someone wearing a hoodie, or in the shoplifting case, we also had an issue where most of our actual data came from Christmas. So we also wanted to make sure it didn't classify as having like a Santa in the background was something that was a classifier. So for this, in our case, what we did with a soccer game was we took out everything that had a scene change and tried to see if like it still had as much accuracy. These sort of things. And all of this is, of course, because, like Henk also was mentioning, the machine learning model does not know what a hand is. It does not know what any of these things are, even these generative models. It knows that a set of like skin-like things huddled together like this look approximately like a hand. Therefore, it will generate things that look to it enough like a hand, but maybe to a human would not be very accurate. The other thing that we had as a little bit of an issue was, what does accuracy actually mean in the case of video? Because you can say an image classification, we can say, okay, so it in 4 out of 5 cases it picked cat when it was cat, and it picked not cat when it was not a cat. But in our case, what happens if it was like 2 seconds off? Is that good enough? Is that considered a hit or a miss? These sort of things. So we tried doing these diagrams where we marked out, this is the actual marking, like these green ones, and this is how much our model thought it was a shot on goal or not. And so we did other visual, so we can, yeah. We did both. We did both. Sort of used audio on the raw footage and on the commentator, and yes, it did make a difference with the commentator too. The only thing was that they also wanted this to apply on the raw data, so they couldn't use the commentator because the commentator would not always be, for example, in Italian, where they would have a very different pitch compared to if it was sort of like a Spanish. Well, Spanish and Italian, I think, are fairly similar in the ways to view soccer, but a Swedish commentator would be completely different. This was an Italian company, so this is why I'm mentioning this. But yeah, so we actually scrapped like the commentator for a number of different reasons like that. But we looked at this and we kind of like set a threshold for when we thought it was okay and not okay. But this was a very difficult piece of the puzzle to figure out like the actual accuracy. So one of the things that we did was we had this marker, like so we put it on as an overlay of the video, sort of showing when there was something interesting going on, it would go very green, and if there was not, it would go not so green. And then we could have humans actually go through and look at it and see, did it feel right? Like, did this level of excitement match your level of excitement of the game? So that was partially also how we measured it. You see, this is like super low res because we actually used a very low res video input in the end in order to be able to process very fast. Then you also have to be sort of cautious that in this case, maybe not so much, but in a lot of cases, you have to be cautious that it learns what it needs to learn. So this was, I have a whole sort of talk on AI and ethics, but this is one that's a little bit funny where they use technology to figure out if someone is jaywalking, and they ended up sending this woman a lot of fines. She also had that on the bus, so she was very often, yeah. So these things can happen, and because of that, whenever you create a model of any kind, you need to always consider having a human in the loop. So in our case, our human in the loop is here, someone who actually watches the end highlight reel or puts together the highlight reel based on the different sections. And yeah, with that was sort of like the project from start to end of video action detection. So yeah, go out and do video action detection. You have all the basics. No, but I would deeply recommend working on on projects like these because they're super fun. Any questions? Yeah. I don't think before, like, they were actually pretty matched to the center, but that would have been interesting. We ended up actually not necessarily predicting so much shots on goal, but in the end, our model ended up predicting interesting events. And we went in with the thought of predicting shots on goals, but we ended up more with this excitement meter, mainly because of the 3D CNN and the audio that seem to be less accurate at the actual events, but more accurate at the highlights, sort of. Yeah. Well, it's it's hard to say, but like we were pretty. I feel like not, because it pretty well matched when it was and when it wasn't an interesting event. So now, having said that, UEFA games are sort of um, they're filmed in very specific ways and with very similar, like most of them have a very similar pattern and things. So I would say that it is definitely a model that would not work on Little League games by any means of, like, there is no stretch of the imagination that it would. So in that sense, yes, it's overfitting to the scenario, but that was good enough for us. Okay. Well, yeah, that's interesting. So we worked on it for we worked on sort of like the exploratory phase. We didn't actually work on putting the model together in the first stage, and that was, I think, 3 months. And then we ended up working on a training project with them for another 4 months. But that was not even the full extent of this whole thing. So yeah, it's quite a lengthy operation. It's not you put this together in your free time, and yeah. Hmm. Definitely not. So when we work on machine learning projects, we usually do something called a feasibility study, where we do like these models or set of models, like in this case, where you go through and you say, okay, so, and in a lot of cases where we've done machine learning models with customers, we've even come out of like the exploratory phase and said, yeah, we're not ready. We don't have enough data. We don't have, like, what you're trying to predict is non-predictable. with the data that we have. So in one case, for example, we were trying to classify whether or not they had a certain set of screws, or like not even a certain set of screws, if they had different screws and different things as inventory on different sites. So they would go around with the camera and kind of like scan the area, but we didn't have enough data, so we ended up creating 3D models of the data. So sometimes your feasibility study kind of also shows that you need to do something different to gather that data, or maybe create like an app that lets users input data that you need for training. So yeah, very very seldom do they have the data to begin with, I would say. Cool. Yeah. Mhm. So some of them are free. Some of them you have to pay for commercial use. One pre-trained model is, of course, cognitive services. So it depends on what you need. But a lot of times, for simpler, like if you want to do something yourself for your own, and like do your own personal model, or even for like a small thing, um, there's like RetinaNet weights for 80 categories and things like these. Then you can actually download together with Keras. So Keras has a lot of pre-trained models. It takes a while to download the weights. They're quite big, but yeah. Okay. Well, thank you so much.